What the finite cell method says is that instead of trying to subdivide my geometry into these little elements that follow the boundaries, we take our geometry and place it into an imaginary box.
There's a bunch of CT data and it's hard to analyze, but this is, it gives you a way to take it and instantly use it. Even a step further, I mean, on top of just designing generic implants, you can almost directly just take the anti-scan, so to speak, the opposite of your CT scan to recreate exactly what's missing in their bone.
For those AI enthusiasts out there, whether the graph neural nets is something that would be better compared with using neural nets to assess the simulation results, because everything is already in a nice grid structure. So Laszlo, how does the hyperganic quasi-meshless simulation compare and contrast with the way that normal simulation is done in other softwares?
All right. So basically, imagine that, I don't know, you are driving over a bridge and, this bridge was designed by some engineers. And if you're lucky enough, these engineers were actually worrying about whether that bridge will hold or not. And what they would probably do during the design process of the bridge is at one point, they would probably set up a finite element model of that bridge, just to assess what would happen if you drive over that bridge. Like, let's say your car is here in the middle, it has some weight, and they would want to figure out, okay, how the bridge is going to deform. And what the finite element method does is that it says, okay, I am going to subdivide this bridge into many, many, many little subdomains called elements. You see these little quadrilaterals here. And each element obeys the basic laws of mechanics, meaning that if I fix some part of this element and then I push it on the other side, it's going to deform by it's going to deform, it's going to displace a little bit. And if I carefully piece all these elements together such that they form a so-called mesh, the sum of all the elements, I can represent the behavior of the entire system. So, this is probably something that you would expect from a simulation like this. If you piece these elements together and run the simulation, you will see a deformation plot and stresses like that. Now, this process of mesh generation, we already spoke about. It's quite tedious and people don't really like it, especially because there are quite a lot of requirements that a mesh needs to satisfy in order to make a good analysis. So let's not go into too much details about this, but it's not an easy process. There are actually really conferences about mesh generation. And there were even studies about this done in the US some time ago, where they really tried to understand, okay, what is really the effort that goes into preparing the geometry for a simulation. And actually, it looks like that quite a significant amount of engineering work would go into just preparing the geometry and generating a mesh on it. So, if you think about it, this was something extremely simple, but imagine trying to mesh a geometry like this. This is something that, I don't know, probably a simulation engineer would hand in his notice if he would have to simulate this, or it would definitely be a very long project to run a simulation on something like this. So what the finite cell method says is that, okay, instead of trying to subdivide my domain, my geometry into these little elements that follow the boundaries of my geometry, why don't we do something different? Why don't we say that we take our geometry, our little bridge, and place it into an imaginary box, into its bounding box. And imagine that this bounding box is filled with some material which is extremely soft. It is so soft. It's like, sorry for the analogy, it's like toothpaste, or something which is very soft. And instead of making a mesh that follows the boundaries of the object, let's make a mesh that follows the boundaries of the box. So something this around the geometry here. So instead of meshing the object, let's mesh the bounding box. And meshing the bounding box is really trivial, you know. It's really just, as I said earlier, it's really just making layers of little cubes and stack them on top of each other, and we have a mesh on our box. So it's basically, the basic idea is that you extend the boundaries of the domain of interest such that it forms a box, and you examine the union of the original domain and this extension domain, the embedding domain. Sometimes people call it like that. And this really is a trivial task. And if you do it right, there are some caveats that you need to take care of. Let's say you can really arrive to the same result as you would arrive with a conventional body conforming mesh representation. So you see here this animation now. If this is a finite cell analysis, if we do the same analysis on the bridge that we were doing before with the body conforming mesh, we see that we get the same results. And you also see that actually in the background, the entire mesh is deforming, but we really don't care about how this extremely soft material is deforming. We only care about how the hard material, the bridge material, is deforming. Does it help? Yes. The explanation?
Yeah, I think I asked this question for most of the listeners because the concept is quite different from how the normal meshing occurs. So we call it quasi-meshless, so we know there's still some meshing involved. But I think this gives a good illustration to the listeners to why this approach is going to be much faster than the conventional one.
Yeah. Great. I hope it helps the understanding of how this method works. Right. So now, as I was warning you, there are some equations about this, but we don't necessarily have to talk about them. But so if you feel like you can also just cut this out. But basically, then the without really going too deep in the theory of the finite elements, at one point when you run a finite element analysis, you compute integrals, and integral is to create something which is called the stiffness matrix of your system. And the generation of the stiffness matrix requires the evaluation of integrals that look like this. And it turns out that you can massage this integration process a little bit and formulate it in a way that inside your integral, you can incorporate the information about your geometric model. So you can basically say, okay, everywhere where there is material, I have the entire full stiffness of the material, and everywhere where there is no material, so we are in this little embedding domain, I can multiply the material with some very low numbers to represent the almost infinite softness of the material, which surrounds our geometry of interest. And then this can really go into the integral and the numerical quadrature, which is responsible for evaluating these integrals. It's actually it's almost a study on its own. How can you do this integration right? But we don't really have to go into details about that. But basically, this also kind of ensures that the equations that you are solving at the very end are the same equations that you solve, and it's probably easier to buy a bigger machine if you want to simulate something more complex than hire 3 extra engineers just because you have to mesh something which is pretty difficult to mesh, So I think it scales better sometimes, especially if you are a company and you don't need to do complex analysis every day, but maybe every 3 months, then you can rent a machine that is able to run these analyses just for those 1 or 2 days when you are running these analysis, and then you are done. It's not that you really have to have a meshing expert in-house who can, you know, answer all the weird questions that can pop up when you are meshing.
Right.
So I think it's pretty cool.
In traditional FEM, for certain obviously packages, you're operating on surfaces and you're mapping and you're meshing the surface and you're watching basically the interaction of the nodes at each point, and that's what's returning your deformation, say, for example. Whereas here, if we're working with voxels, I just wanted you to maybe mention and speak on the fact that because we're working directly with volumetric information, how this helps with, say, the bone study, where you can apply properties a little bit easier and you can apply different properties and actually have it so it's contained internally within the material, instead of just, say, you know, setting an overall material for individual beams and meshing things and getting towards multi-material simulations, which is quite tricky, especially in conventional simulation techniques.
Yeah. Right. If you don't mind, I will share my screen again. So you might see now a different software called ParaView, but yeah, it's just we are looking at the problem through ParaView because it's easier to go through many steps of a simulation workflow starting from CTs in ParaView. But so what you basically, as you have seen on the slides already before. If you imagine this domain, this embedding domain, the bounding box, and you imagine that it is meshed into a regular grid of elements, you very quickly realize that one slice of these elements, it really resembles an image, right? It's just a regular grid, 2D slice of intensity values at the end, right? It's like an image. It's like a bitmap. Then if you stack all these bitmaps together, what you have is something which actually is basically a CT scan, right? In CT scan, you also just have many slices stacked on top of each other, each slice representing a bunch of intensity values that tell you whether there is material or no material at different regions of the slice. So what you see here now, I mean, it's not super exciting, but what you see here now is one such domain. You know, it's a CT, it's the bounding box of a CT scan that consists of many pixels or many voxels that you see here, bounded by these white edges. And if we, for example, would look inside of one such a CT scan, if we, by removing parts that are like completely dark, completely irrelevant, what we would end up with is something that looks like this, which I think is probably more familiar to you if you think about X-ray pictures or maybe even CT scan pictures. So what you see here is basically a CT scan of a femoral bone. Sorry, a femoral bone. And if we zoom in, you see that there are dark areas, and then there are brighter areas, and there are darker areas again, which are basically intensity values. So wherever we are dark, we know that there is no material. It's something which is very soft. Where if we go towards brighter and brighter areas, we see that there is material, there is a bone, there is even more bone, it's even brighter. And then as we cross again towards the middle of the bone, we see that it becomes again darker and darker. And that sort of also represents, this intensity sort of also represents how stiff the material is, right? So here in the dark and here in the middle where there is the bone marrow, there is something which is extremely soft, you know. It's something that cannot really sustain loads. It cannot really carry mechanical loads. And here in the bright areas, you have something that can carry mechanical loads. So if you try to push it here, then it's gonna resist that push, and there is gonna be some kind of a stress inside. And the good thing about the CT scans is that you can, looking at these intensity values, you can map these intensity values to real stiffness properties. So there are relationships that really establish a relationship between an intensity of a voxel to a Young's modulus. So I feel, I'm not 100% sure about how exactly these relationships look, but basically they really establish. They really say that, okay, wherever we are in the dark area, it's something soft, and wherever we are in the light area, it's something hard or something stiff. And now, if you just think back for 1 second to the idea of the finite cell method, where we say, okay, these stiffness matrices of the elements, when we compute them, we can multiply the material properties by some factor to control the stiffness of individual elements. This is exactly the same what you can do also here in the case of the CT scans. When you create the element stiffness matrices, you can really say, all right, in the areas where there is dark material, where there is low stiffness, the element stiffness matrices will have a lower contribution, or they will have a lower values. And wherever we are in the high intensity areas, the element stiffness matrices will be stiffer, or the elements will behave stiffer. So you can really establish a relationship between CT scan intensities and stiffness of your material and the resulting stiffness matrix of your entire system. This is how we can really incorporate information from CT scans into the mechanical simulation. And if you think about it, if you would want to simulate this with conventional finite elements, what you would have to do is first somehow extract the surface that goes here. I hope you see the mouse. Extract the surface that goes around the bone, just to have something that you can then eventually mesh, right? So first you would need to somehow run some kind of a surface extraction algorithm, pray that it works out and the program doesn't crash in the process of extracting that surface. And then once that surface is there, you would have to mesh it, and then you would have to somehow think, okay, how now I have a mesh, but I have the CT scan as a separate object, as a separate file, and now I have to somehow take the values from the CT scan, transfer it onto my mesh, but oh no, the elements are not really coinciding with the voxels, so I need to somehow interpolate in between. So it can get very difficult very quickly, which I think is doable, and probably people do it with relative ease, but there is a much easier way if you think about the regularity of the data and how well it fits with the kind of simulation approach that we are doing here in Hyperganic. Right, and so this is how you would incorporate the volumetric data from a CT, for example.
You're giving it like a direct mapping, so to speak. And as opposed to say, when in traditional, you've got to do all of these additional steps. So it makes it more available to utilize these the CT data, which we have a plethora of in the world. There's a bunch of CT data, and it's hard to analyze. But this is it gives you a way to take it and instantly use it.
Yeah, exactly, and then exactly, and then if you think about it, it's a lot of manual work is gone. So you don't need to do that, which of course means that less expertise is required, which could potentially mean that people who are not simulation experts will also be able to conduct analysis like this. So I think it's a very helpful step to bring computations like this closer to non-computational experts or non-simulation experts.
I think it's really interesting because how in Hyperganic, a lot of the things we do, we often like to tie together with additive manufacturing. But here you can see that, just the simulation capabilities, we can do these kind of biomedical imaging and how it can extend beyond just the realm of additive manufacturing.
Yeah.
because as you mentioned, the analogy between these kind of bitmaps to voxels to having this kind of stiffness vectors and the stiffness matrix is going to be quite powerful, especially when talking about these kind of CT scans. So I was just wondering, how can some of these concepts be translated to additive manufacturing in your experience?
So if we stay with this example, one pretty direct consequence of being able to do computations like this, and also the fact that you are able to, what if this bone, not strong enough anymore and we want to fix it? We probably will need an implant. So you could say, all right, why don't we try to put an implant inside and see whether so here you see, for example, part of that bone was cut off and an implant was inserted. I'm going to make this bone disappear for a second. The thing here, it is really true that one size doesn't. There are short people, tall people, men, women, different bone structures, different ages. Probably family of implants will not be perfect for everyone. But of course, there is a reason why there is not very straightforward. So probably you don't want one implant for every patient, unless you go for something that is based on additive manufacturing, right? Because additive manufacturing is actually pretty good for all right, I could maybe start from one kind and then look at how that implant shape can be inserted in that bone, and then maybe even look at how that implant plus bone together will deform. Look at the stresses, how the stresses would look like in this situation, and then make a decision. Is it good enough or is it not good enough? If it's not good enough, what do? We can change how the implant is inserted, or we can try to rotate it or change the position of it. But actually, we could also change the shape of the implant itself. And the good thing is that now you can get an almost instant feedback about what would happen if I would change the shape of the implant. How would the stresses redistribute, or how the whole deformation pattern would change. And I think this is something that is probably with Hyperganic extremely easy to do. Come up with an army of different implants.
Right.
Small lattice, big lattice, and
right.
lattice oriented in one direction, lattice oriented in the other direction. I think this is a definitely a very exciting and interesting area where you could really benefit from the power of creating very individualized implants, and also getting a very quick feedback about how that implant would behave. And this all based on this data specific to the very patient who's sitting in front of you, whose CT scan you are looking at.
And I think one thing that is going to be very interesting for the biomedical engineers out there is that the fact that for different designs, different porosities, different lattice structures, the amount of osseointegration and how the bone cells interact with your implant is also going to matter a lot. So this kind of parametric design where you are able to optimize for porosity, for the structure is going to be really beneficial in additive manufacturing.
Taking it even a step further, I mean, on top of just designing generic implants and changing them and changing how we implant them, you can almost directly just take the anti-scan, so to speak, the opposite of your CT scan, to recreate exactly what's missing in their bone. We don't even have to start from a standardized tip implant and start optimizing from there. We can quite literally recreate the hole or the lack of mechanical properties that exists in their bone, reshape or create the object out of voxels, and then start that optimization process again, which is a far more, almost, you can imagine being a patient sitting there and someone goes, here's what's missing, here's what we're going to put in you, and we've run a couple simulations and it's already improved from what you're currently dealing with to properties that are much more like when you had a full bone and there was no damage, there was no there was no issues internally. And it gives that extra dimension to the customization that you get from taking that data directly from CT scans.
Yeah, definitely. I think it's very, very exciting, and it's probably also a very much uncharted area. A lot of possibilities there.
Mhm.
Nice. Any closing thoughts? Otherwise, we say bye-bye and
I
Yeah.
have one closing thought, and maybe Laszlo, I've not asked you this before, but I realized that it just came to me earlier, and I realized that this finite cell method, because everything is in a nice grid structure, I think I'm not sure if for those AI enthusiasts out there, whether the graph neural nets is something that would be better compared with normal neural nets in terms of trying to assess using neural nets to assess the simulation results. If it's something that we could exploit rather than the normal conventional neural nets, because everything is already in a nice grid structure.
Yeah, actually, you are thinking in a very good direction. I think exactly this regularity of the data makes it also very well suited to throw all kinds of novel machine learning techniques on them. For example, neural networks, and I think there was also actually quite some interesting experiments done in this direction recently in the simulation group. I don't want to spoil all the results of it, but there are really interesting and promising approaches in this direction. So yeah, definitely it's a very viable and potentially possible way.
Yeah, and just literally again to add on that point, especially with the machine learning, the big issue again, as you've said, with normal traditional simulation is the time it takes to mesh. And as we know with machine learning, it's all about data. So here we're getting in a situation where we don't have to deal with the timely process of meshing something. We can iteratively simulate, iteratively pull that data, and it means feeding these machine learning models data is becoming far easier. It's much more automatic process compared to constantly every time you change your implant or you change your lattice, you've got to remesh it, you've got to make sure it's all set up correctly so you're going to get good results. Here we can just run loops, pull data, feed it into the machine learning models, and it's a much faster way to kind of work out what is effective and what isn't effective when it comes to training stuff in AI. So it's going to be really exciting to see where it goes as we move forward.
Yeah, definitely. So as you say, the fact that now this loop can be closed and tightened, and the human factor can be removed from this feedback, it really allows us to do much more than it was possible before. So it's super exciting, super interesting.
So yeah, thank you so much, Laszlo, for spending the time with us today. It's been really
thanks.
insightful.
Yeah, no, thanks for having me here in the office round. We should do it more often.
Yes. All right, then have a nice weekend, because tomorrow is Good Friday and I believe a holiday for you guys.
Enjoy the holidays.
Yeah.
Yep. Thanks a lot.
Right.
Thanks a lot.
Bye-bye.
Bye-bye. Ciao.
See ya.